It carries with it a breath of alien chemistry, enough carbon dioxide to awaken the atmosphere of a dead planet, and its path is no casual drift through the void. This interstellar visitor, catalogued as 3-1 Atlas, is moving toward Mars with the kind of precision that evokes a Swiss atomic clock. The timing is uncanny. Only days after NASA's announcement of potential biosignatures locked in ancient Martian stone, this object is set to pass within 30 million kilometers of the red planet, an astronomical hair's breadth on the scale of interstellar distances. And all the while, it slips behind the Sun from Earth's vantage, hidden from most of our telescopes as though choosing the cover of light itself. Astronomers murmur in awe. Conspiracy theorists roar with certainty. Because in a universe where randomness rules and gravity writes crooked lines, nothing should be this exact. Something is unfolding in Mars's orbital neighborhood, something that shakes our sense of cosmic chance. What Atlas is carrying, and why it has arrived at this precise moment, may yet prove to be the most unsettling discovery humanity has ever faced. For more than 4 years, NASA's Perseverance rover has been crawling across the floor of Jezero crater, digging quietly into the Martian past. Day after day, it has drilled into the ancient mudstones, a patient archivist of a world long gone. And then, in July 2024, it delivered something extraordinary. From a site near the Bright Angel outcrop, a sample known as Shieva Falls revealed textures unlike anything scientists had ever seen on Mars. Patches of mineral staining that researchers began to call leopard spots. At first glance, they look like curious patterns pressed into stone. But beneath their beauty lies something much more profound. Perhaps one of the most compelling traces of ancient life ever uncovered on the red planet. To understand the weight of this discovery, you need to know what a biosignature candidate really means. Imagine nature leaving behind an autograph, chemical fingerprints, or structural traces etched into the record of rock. That is what scientists hunt for. In this case, the leopard-spotted textures were found to contain minerals like vivianite and greigite. On Earth, these compounds often form in the presence of microbial activity. Yes, they can appear through geological means alone, but their abundance in Earth's fossil record is usually tied to biology. It is as though Perseverance had stumbled across ancient footprints pressed into Martian mud. Only these footprints may have belonged to invisible organisms, thriving 3.5 billion years ago in waters now long vanished. To grasp the setting, we must travel back through time. Jezero was not always a sterile, dust-scoured basin. Billions of years ago, this crater held a great lake, fed by a branching river that fanned out into a delta. The layered sediments that Perseverance now samples were once part of this living system. Deltas are nature's filing cabinets, preserving traces of organic chemistry in exquisite detail, capturing the whispers of ancient life and sealing them away in clay. If Mars ever hosted biology, Jezero was one of the likeliest places to find its echoes. Yet even as scientists celebrated this tantalizing biosignature, another story was unfolding, one that began far beyond Mars. On July 1st, 2025, the Atlas telescope network caught sight of something entirely unexpected, a cosmic visitor racing through the dark between the stars. It was given the name 3I Atlas, the third confirmed interstellar object ever detected by humanity. Atlas, the asteroid terrestrial impact last alert system, was built as a planetary guardian, scanning the heavens nightly from observatories in Hawaii, Chile, and South Africa. Its purpose is to catch asteroids that could one day menace Earth. But on that July night, the system found something stranger. The object it detected was not bound to our Sunday. Instead, it rode a hyperbolic trajectory, a flight path that carried it from the deep interstellar void straight through our solar system on a one-time visit. Unlike planets and comets trapped in elliptical orbits, 3I Atlas moves with the freedom of an exile, destined never to return. Here's what makes the heart beat faster. While NASA was announcing Mars's strongest candidate for ancient life, this interstellar wanderer was already on course to sweep close past the red planet itself. The timing felt uncanny, as though two stories, one carved in stone, one streaking through space, were converging. The science, however, is cautious. 3I Atlas shows no signs of being artificial, no glint of alien machinery, no whisper of radio transmissions, no sudden course corrections to suggest intelligence. By all accounts, it is natural, and yet its chemistry holds mysteries that tug at the imagination. Observations from the James Webb Space Telescope and NASA's SPHEREX mission revealed a coma dominated not by water vapor, as one would expect from an ordinary comet, but by carbon dioxide. The ratio was startling: 8 parts CO2 for every 1 part H2O. Instead of a dirty snowball bleeding water ice into space, here was a body exhaling great clouds of carbon dioxide, like breath crystallized in the cold of interstellar night. Astronomers also noted a faint greenish glow around its coma in September, an auroral shimmer, possibly caused by dicarbon or cyanide compounds, streaming from its surface. These are not alien substances in themselves, but their abundance in an object from another star system raises compelling questions. What kind of world forges such a comet? What distant chemistry shaped this emissary before it was hurled across the gulfs of space? Inevitably, the internet lit up with theories: alien probes, engineered projectiles, even purposeful tools of planetary terraforming. NASA's voice has been calm, grounded in data. They remind us that every observation so far aligns with a natural explanation: a comet with unusual composition, no danger to Earth, no evidence of technology. But even the most disciplined scientists admit that some coincidences demand reflection: the timing, the chemistry, the proximity to Mars, precisely as we announce possible traces of life there. If one wanted to jumpstart Mars's atmosphere, to nudge it back toward habitability, what better courier than a comet heavy with greenhouse gases? Carbon dioxide is exactly the agent that could thicken Mars's thin sky, trapping sunlight, warming the surface, and setting the stage for the planet's slow rebirth. This is speculation, yes, dreaming stitched to science. And yet science itself is born from the tension between skepticism and wonder. Sometimes the universe presents patterns too striking to ignore, alignments that whisper of stories larger than our own. 3I Atlas is one such pattern, a thread that ties together the search for life in Martian mud and the arrival of a wanderer from the stars. So we stand at a crossroads of discovery. In one hand, the fossilized clues of microbes that may have stirred in Martian waters billions of years ago. In the other, the chemical exhalations of a comet older than our sun, passing by as though to remind us that life and chemistry are not confined to Earth. Two stories, unfolding in parallel, may yet converge into one narrative. A cosmos alive with possibility, where every rock, every comet, every crater holds a piece of the puzzle. Buckle in. The universe is speaking in patterns and signatures, in dust and gas, in stone and ice. It is inviting us to listen, to wonder, and to ask the question that has haunted us since the first time we looked up at the night sky. Are we alone, or has life always been out there, waiting for us to notice? To understand why 3I Atlas is such an extraordinary traveler, it helps to first imagine what it means for an object to follow a hyperbolic path. Picture tossing a ball upward. It rises, slows, hesitates, and falls back to Earth, forever bound by gravity. But if thrown with unimaginable force, strong enough to break free of Earth's grasp, it would never return. On a cosmic stage, this is what a hyperbolic orbit represents. Freedom from a parent star, a path leading only outward into the deep. Astronomers describe the shape of an orbit with a number called eccentricity. A perfect circle holds the value of 0. Earth's slightly stretched oval registers at 0.017. Push that figure past 1, and it signals an escape trajectory, an orbit that no longer curves back but opens outward. 3. Atlas, with its eccentricity far beyond that threshold, carries the undeniable signature of interstellar origin. It is not of this solar system. It is the third confirmed visitor from another star, following the puzzling Oumuamua in the year 2017 and the more familiar comet Borisov in the year 2019. The first of these wanderers, Oumuamua, appeared elongated, even cigar-like, and exhibited a strange acceleration that ordinary sunlight could not explain. The mystery ignited speculation about exotic compositions and even artificial construction. Borisov, by contrast, looked and behaved like comets we know well, with a glowing coma of dust and gas, flaring in predictable ways as sunlight struck its icy heart. 3I Atlas sits between these two extremes. It bears no sign of engineering, no signals, no impossible dynamics, yet its chemical portrait is profoundly unusual. The James Webb Space Telescope, with its unmatched sensitivity, was aimed toward Atlas soon after its discovery. What it revealed defied the ordinary models. Instead of a halo dominated by water vapor, the coma glowed with carbon dioxide. Measurements showed a carbon dioxide to water ratio of nearly 8:1, one of the highest ratios ever seen in a comet. Ordinarily, comets are described as dirty snowballs, frozen relics from the formation of a planetary system. As they near their star, heat sublimates their water ice, producing familiar tales of vapor and dust. Atlas, however, seems to breathe carbon dioxide as though it were a block of dry ice hissing in the warmth. This departure from expectations suggests possibilities that stretch our imagination. One explanation points to formation. Perhaps Atlas was born near the carbon dioxide ice line in its home system, a place cold enough for carbon dioxide to freeze while water remained in gas form. Another explanation lies in time. After millions of years in interstellar space, relentless cosmic rays may have altered its surface, building a carbon-rich crust that now releases carbon dioxide more readily than water. A third possibility considers structure. If a surface layer of carbon dioxide ice blankets deeper reservoirs of water ice, then sublimation could be selective, skewing the observed chemistry until solar heating digs deeper. Already, additional compounds have been detected: carbon monoxide, carbonyl sulfide, and beneath the surface, hints of water ice. Each new detection builds a more complex story of origin. Independent confirmation from the Sphere-X telescope has reinforced the strange profile, ensuring that what first seemed like an observational error is indeed real. In September, observers on Earth began reporting a striking visual effect, a green glow spreading through Atlas's coma. The emerald tint suggested the presence of dicarbon molecules or cyanide compounds. Such species are not rare in comets, yet their vivid abundance in this interstellar wanderer raised new questions about the chemistry at work in other star systems. The sight of the green shroud lent a spectral beauty to an already remarkable visitor. As with Oumuamua, speculation about artificiality surfaced, but astronomers answered with caution. Dr. Alan Fitzsimmons, a leading researcher in the study of interstellar objects, emphasized that nothing in the data contradicts natural explanations. There are no signals, no engineered geometry, no physics that strain the laws of nature. What there is, instead, is chemistry that does not conform to what our solar system has taught us to expect. The challenge lies in the act of measurement itself. Atlas hurtles through space at 30 kilometers per second, millions of miles from Earth, and yet scientists attempt to analyze its chemistry from faint photons captured through Earth's atmosphere or from orbiting instruments. Early spectroscopic results can be distorted by dust, by atmospheric interference, or by the constantly shifting geometry of its orbit. As solar heating penetrates deeper, ratios of gas release can change quickly, turning one chemical profile into another within weeks. The fact that anything reliable can be measured at all is remarkable. The fact that the data unsettles long-standing models makes it more so. As Atlas continues toward its closest approach to Mars, its chemistry takes on added resonance. Carbon dioxide is not merely a curiosity in cometary terms. It is the main gas in the Martian atmosphere, the very component that once blanketed Mars in a thicker cloak, trapping warmth, allowing rivers to carve valleys, perhaps even creating niches for life. Atlas, by chance or by design of physics, brings with it a cargo of the very substance that shaped the destiny of the red planet. The green glow, the carbon-heavy breath, the eccentricity that marks its origin in another star's nursery together, they form a portrait of strangeness, a narrative not of impossibility, but of surprise. Each detection adds to the sense that the cosmos is far less uniform than once believed. Comets may not all be variations on a single theme, but emissaries of wildly different laboratories scattered across the galaxy. Atlas is natural, and yet it is different. Its path is hyperbolic, its chemistry unorthodox, its appearance ghostly green. It passes through our neighborhood like a messenger, carrying with it a fragment of another system's story, another star's frozen memory. Mark your calendars for October the 3rd in the year 2025. On that date, three first Atlas will sweep past Mars at a distance of roughly 28 to 30 million kilometers. In astronomical units, that corresponds to about 0.19 to 0.2, a sliver of space when measured against the vastness of the solar system. To place this in perspective, the distance is approximately 75 times farther than the Moon is from Earth. On human scales that sounds immense, but by cosmic standards it is an intimate passage. What makes this approach all the more compelling is timing. Just as 3I Atlas reaches its closest point to Mars, it will vanish from view for observers on Earth. The reason is solar conjunction. From our planet's perspective, the comet will move behind the Sun, swallowed by the overwhelming glare of our star. For several crucial weeks, spanning late September through late October, Earth-based telescopes will be blind to its behavior. It will be as though a cosmic drama unfolds behind the curtain of sunlight, a whisper drowned out by the orchestra of the solar blaze. The choreography seems uncanny. Maximum proximity to Mars coincides exactly with maximum invisibility from Earth. If one were crafting a work of science fiction, the plot could not be staged with greater dramatic tension. The comet approaches Mars, hidden from our sightline, free to play out its encounter in private. Later in October, 3I Atlas will reach its perihelion, the point in its orbit closest to the Sunday. That will occur on October the 29th or 30th, positioning the comet just inside the orbit of Mars at about 1.4 astronomical units from the Sunday. This places it in the perfect zone for intense solar heating, maximizing the sublimation of its ices and creating a spectacular display of outgassing, all while hovering within striking distance of the red planet. Yet we will not be entirely blind. The European Space Agency has confirmed that 2 spacecraft orbiting Mars are preparing to seize the opportunity. Mars Express, a veteran mission launched in the year 2003 and the Trace Gas Orbiter, in service since 2016, are expected to attempt direct observations during the comet's flyby. While Earth turns its gaze into solar glare, these orbiters will act as our surrogates, recording whatever secrets the visitor reveals as it brushes past Mars. What could these orbiters detect? The possibilities spark imagination. High-resolution cameras might capture fine detail of the nucleus and the inner coma, features invisible from terrestrial telescopes. Ultraviolet and infrared spectrometers could isolate emission lines from compounds such as cyanide or carbon monoxide, passing out the specific molecular signatures of a body formed around another star. Dust analyzers might even trap particles from the comet's tail, delivering to us the first direct grains of interstellar material ever gathered by human instruments. The prospect is staggering. To hold in our scientific archives dust that condensed around another sun 1 billion years before our own solar system was born, the stakes are enormous. 3I Atlas is only the third interstellar body confirmed to cross our skies. Each such visitor provides a data point for understanding chemistry that unfolded in distant stellar nurseries. The unusually high abundance of carbon dioxide recorded in its coma may illuminate conditions of planetary formation in systems unlike our own. It might show us how diversity in starborn environments leads to chemical recipes very different from those that shaped Earth. But there is another layer of resonance, one that ties directly to Mars itself. In recent years, the Red Planet has entered a new phase of exploration, with discoveries of potential biosignatures in Jezero crater fueling debate about its ancient habitability. Today, Mars is cloaked in a thin atmosphere composed almost entirely of carbon dioxide. 95% of its air is that single molecule. Yet billions of years ago, Mars wore a thicker, warmer envelope. It hosted rivers that cut valleys, lakes that pooled in basins, and possibly even a climate that could sustain primitive life. The atmosphere, however, has been slowly stripped by the relentless solar wind, a consequence of Mars lacking a protective magnetic field. Here lies the poetic coincidence. 3I Atlas, a body unusually rich in carbon dioxide, sweeps past Mars at the very moment humanity is interrogating the planet's lost climate. The comet appears to carry the very gas that once made Mars habitable. Of course, scale demands perspective. A single comet cannot hope to replenish a planet's atmosphere. The total carbon dioxide it holds is minuscule when compared with what Mars has lost over eons. Adding it to the Martian sky would be like pouring a cup of water into a dry swimming pool. Yet the symbolism lingers. Perhaps this is not a one-time event, but a glimpse into a broader galactic process where comets repeatedly seed planets with volatile compounds, nudging climates in directions both subtle and profound. For Earth, there is no danger. 3I Atlas will not approach our planet closely. Its nearest pass to us comes in mid-December, when it will glide by at a distance of about 1.8 astronomical units, more than 168 million kilometers away. That is farther than the Sun itself lies from Earth, placing us beyond any conceivable hazard. The interstellar visitor is remarkable not for threat, but for what it reveals. Geometry only deepens the intrigue. An object born of another star, carrying carbon-laden ices, approaches the very planet whose atmosphere is 95% carbon dioxide. The comet does so precisely as scientists uncover their strongest evidence yet of ancient Martian life. During the key days of its closest approach, Earth cannot see it, and only robotic eyes around Mars may glimpse the performance. In a film script, editors might reject such coincidence as contrived. In reality, it is orbital mechanics. By late November and December, once the comet emerges from behind the Sun, ground-based telescopes will once again take up the chase. But by then, the comet will have passed perihelion. The searing heat of its solar encounter will likely transform its appearance, peeling away surface layers and exposing fresh material. The object we study in December may look nothing like the comet of September, offering an entirely new chemistry set for analysis. The European Space Agency has been candid about the difficulties ahead. Unlike Borisov or Oumuamua, whose passages were monitored more openly from Earth, the timing and trajectory of Atlas make an intercept mission impossible. The velocity is too great, the geometry too unforgiving. For now, we are limited to remote sensing, spectral analysis, and the narrow window of opportunity provided by orbiters circling Mars. Perhaps that is fitting. Some mysteries arrive not to be grasped, but only observed. Fleeting visitors who pass through our skies and leave us with fragments of story. 3I Atlas, carrying its carbon dioxide-laden breath and its alien heritage, will sweep past Mars in October, while Earth watches blindly from the far side of the Sunday. It is a drama of coincidence, geometry, and chemistry written across millions of kilometers, unfolding whether we are ready or not. Mark your calendars for October the 3rd in the year 2025. On that date, 3I Atlas will sweep past Mars at a distance of roughly 28 to 30 million kilometers. In astronomical units, that corresponds to about 0.19 to 0.2, a sliver of space when measured against the vastness of the solar system. To place this in perspective, the distance is approximately 75 times farther than the Moon is from Earth. On human scales, that sounds immense, but by cosmic standards, it is an intimate passage. What makes this approach all the more compelling is timing. Just as 3I Atlas reaches its closest point to Mars, it will vanish from view for observers on Earth. The reason is solar conjunction. From our planet's perspective, the comet will move behind the Sun, swallowed by the overwhelming glare of our star. For several crucial weeks, spanning late September through late October, Earth-based telescopes will be blind to its behavior. It will be as though a cosmic drama unfolds behind the curtain of sunlight, a whisper drowned out by the orchestra of the solar blaze. The choreography seems uncanny. Maximum proximity to Mars coincides exactly with maximum invisibility from Earth. If one were crafting a work of science fiction, the plot could not be staged with greater dramatic tension. The comet approaches Mars, hidden from our sight line, free to play out its encounter in private. Later in October, 3I Atlas will reach its perihelion, the point in its orbit closest to the Sunday. That will occur on October the 29th or 30th, positioning the comet just inside the orbit of Mars at about 1.4 astronomical units from the Sunday. This places it in the perfect zone for intense solar heating, maximizing the sublimation of its ices and creating a spectacular display of outgassing, all while hovering within striking distance of the red planet. Let us state the coincidence clearly, without exaggeration. In September of the year 2025, the National Aeronautics and Space Administration announced the detection of possible biosignatures in Martian rocks. The announcement focused on leopard spot textures that might represent the strongest evidence yet for ancient life on Mars. Only weeks later, the interstellar comet known as 3I Atlas, rich in carbon dioxide, would make its closest pass by the red planet before slipping behind the Sun, vanishing into a stretch of weeks where no telescope on Earth could follow it. Every scientist is trained to remember that correlation does not equal causation. Yet in a universe where timing so often feels weighted with meaning, where patterns emerge even from chaos, coincidences invite examination. The rational explanation remains simple. Interstellar bodies arrive from unpredictable directions at unpredictable times, governed by the relentless mathematics of celestial mechanics. 3-1 Atlas began its journey in some distant stellar neighborhood millions of years ago, long before humankind existed, let alone developed instruments capable of teasing out Martian biosignatures. Its hyperbolic trajectory was set by the gravitational tides of its birthplace, modified by close stellar encounters during a voyage that spanned interstellar distances. Hyperbolic paths do not bend to wishful thinking. When astronomers calculate an orbital eccentricity greater than 1, they are measuring something elemental about an object's history and its fate. 3. Atlas is unbound to the Sun, a visitor carrying excess velocity that ensures it will leave this system forever. It is not a captured object, angled deliberately toward Mars, but a traveler on a one-way course shaped by physics that pays no attention to the calendars of human discovery or to the biology of a neighboring planet. Still, from a narrative perspective, coincidences rarely stand alone. In thrillers and speculative tales, they layer atop one another until the weight of circumstance demands attention, so the geometry must be examined. 3I Atlas will reach its closest approach to the Sun around the 29th or 30th of October, positioning itself just inside the orbital path of Mars at roughly 1.4 astronomical units. This is the very zone where solar heating reaches peak intensity, driving volatile ices into jets of gas and dust. At that moment, the comet will be nearest to Mars, and from Earth's vantage point, it will slip behind the Sun into a period of invisibility. Solar conjunction creates an observational blind spot, a span of several crucial weeks when even the James Webb Space Telescope and the largest ground-based observatories will be unable to watch what unfolds. The chemistry of this comet lingers in every discussion. A coma dominated by carbon dioxide is rare, though not impossible. And yet carbon dioxide is precisely what Mars needs most, if its atmosphere were ever to be restored. Today, the red planet's atmosphere is already 95% carbon dioxide, but its pressure is less than 1% of Earth's, leaving the surface exposed to cold and radiation. Any process capable of delivering additional greenhouse gases could, in theory, help reverse the long atmospheric loss that transformed Mars from a world of flowing rivers into the frozen desert we see today. For the public, confusion sometimes arises between interstellar visitors and interplanetary missions. 3. Atlas is not a spacecraft, not a vessel that can be aimed or redirected. Its course is dictated by the immutable pull of gravity, by encounters with stars across millions of years. There are no course corrections, no hidden propulsion, no intelligent hand guiding its motion. It is chemistry and ice bound together, following the mathematics set down by Isaac Newton and Johannes Kepler. The position of the National Aeronautics and Space Administration has been clear from the beginning. Every observation of 3I Atlas is consistent with the natural behavior of a comet. No signals have been detected, no geometry suggests construction, no maneuvers indicate intelligence. It poses no danger to Earth and shows no evidence of being anything other than a frozen body shaped by natural processes. And yet the timing feels charged with significance. On one stage, we have the story of Martian rocks bearing possible signatures of biology, relics of a world that might once have been alive. On another stage, we have an interstellar comet, heavy with carbon chemistry, arriving at Mars precisely when scientists are re-evaluating the planet's potential for life. Separate narratives intersect in a way that the human mind instinctively binds together. A thought experiment stretches this line of speculation further. What if atmospheric engineering is not merely the province of science fiction? What if the chemistry carried by 3I Atlas carbon dioxide abundant, timed to reach Mars at the moment of closest pass, represents not coincidence but design? Not design in the sense of deliberate construction by extraterrestrial beings, but design in the broader sense of cosmic selection. Perhaps the universe produces interstellar messengers whose chemistry supports the atmospheres of planets, nudging them toward conditions more favorable for habitability. Perhaps the same processes that sculpt life-supporting environments also generate the means to replenish them. This line of thought strays into speculative territory, but it illustrates why timing can feel suspicious, even when the mechanics are purely orbital. 3I Atlas remains a natural object, unbound, moving with hyperbolic certainty through our solar system. Its chemistry is unusual, its approach dramatic, and its appearance on the cosmic stage coincides with discoveries that force us to reimagine Mars's history. It is worth noting that carbon dioxide and water, the dominant elements revealed in the coma of 3I Atlas, are also the very ingredients from which planetary atmospheres arise. These are the molecules that enable climates to stabilize, clouds to form, and, under the right conditions, life to emerge. The ratio between them may appear unusual, but the chemistry itself is precisely what any imagined terraforming project would seek. Greenhouse gases for warmth and liquid water to anchor biology. Yet the reality of Mars resists such dreams. The red planet lacks a magnetic field strong enough to protect an atmosphere from the stripping force of the solar wind. Even if every volatile particle carried by 3I Atlas were somehow transferred to Mars, the long-term erosion mechanisms would grind away the temporary enrichment. Atmospheric engineering on this scale remains speculative, more thought experiment than plan. Still, the story of 3I Atlas tempts us to think beyond a single event. This comet is the third confirmed interstellar visitor in less than 10 years, hinting that such travelers may be far more common than once assumed. As telescopes grow sharper and surveys more comprehensive, it may become clear that the galaxy regularly delivers packages of volatile chemistry across interstellar boundaries, playing a role in planetary evolution that we are only beginning to recognize. From here, the narrative diverges along two tracks. The cautious scientific path interprets 3I Atlas as an unusual but natural comet, its encounter with Mars nothing more than orbital happenstance. The data is consistent, the physics sound, and no extraordinary explanation is required. The speculative path allows broader possibilities, not design, not intent, but patterns that suggest a hidden rhythm in cosmic processes. Both tracks converge on a shared recognition that this is a moment where traces of ancient Martian biology and the volatile chemistry of an interstellar comet cross paths, pressing us to reconsider the line between coincidence and significance in the unfolding story of the universe. The gaps in our knowledge about 3I Atlas provide fertile ground for extraordinary theories to flourish. Limited visibility during its crucial encounter near Mars, evolving spectroscopic data as the comet warms, and the inherent challenge of interpreting chemistry at interstellar distances, each uncertainty becomes soil in which speculation can take root and spread. From an observational standpoint, the situation is stark. 3I Atlas was discovered on the 1st of July in the year 2025, giving astronomers fewer than 4 months to study it before solar conjunction hid the object behind the sunday. That is barely enough time to secure basic orbital parameters, let alone perform a detailed analysis of composition on a body racing through space at 30 kilometers per second. The online debate that followed unfolded in predictable ways. Social media algorithms rewarded extremes, amplifying claims about alien craft and hidden conspiracies, while burying careful scientific commentary beneath waves of engagement-optimized content. Influential figures with millions of followers shaped global perception of 3I Atlas through a single sensational post, regardless of their expertise or lack thereof in astronomy or astrobiology. The National Aeronautics and Space Administration responded with steady discipline. The strategy was textbook: acknowledge the unusual findings, explain plausible natural causes, and emphasize that no evidence pointed to artificial origin or threat to Earth. Dr. Paul Chodas from the Center for Near-Earth Object Studies stated clearly that all data remained consistent with a natural comet, chemically unusual, but still within the realm of possibility. This situation differs from earlier alarms in one important way. The detection networks that spotted 3-1 Atlas are designed for speed and transparency. The Atlas telescope system, which first noticed the comet, publishes observations within hours. That makes it nearly impossible to hide or suppress data about potentially hazardous objects. If the comet were making course corrections, emitting structured radio signals, or revealing geometric perfection, the evidence would be instantly available to astronomers worldwide. Transparency both reassures and disappoints, stripping away the romance of secret cover-ups in favor of a prosaic reality. Astronomy is now global, automated, and intensely collaborative. The physics of interplanetary travel further constrains speculation. 3I Atlas follows a hyperbolic trajectory, already moving beyond the Sun's grasp, and its distance from Earth makes interception impossible with present-day spacecraft. The European Space Agency has underlined this limitation. Humanity simply lacks the technology to match its velocity or trajectory on such short notice. Direct sampling is off the table. What remains are remote observations, spectral analysis, and whatever information Mars orbiters might capture during the October passage. The challenge resembles trying to guess a person's origin, profession, and intentions by watching their silhouette pass by a distant window at night. These very limits our inability to get close, to touch, to directly measure, create the opening for both healthy skepticism and unhealthy speculation. The criteria for artificiality are specific: non-Keplerian maneuvers suggesting propulsion, narrowband radio transmissions pointing to intelligence, geometric structures visible in high-resolution imaging, or chemical patterns that cannot arise naturally. None of these have appeared. The orbit is cleanly hyperbolic. Radio silence remains unbroken. The coma is diffuse, lacking sharp edges or architectural hints. Even its puzzling chemistry, while striking, fits within theoretical models of comets born in other stellar nurseries. Yet absence of evidence does not always feel like evidence of absence. The deeper question is whether we are observing enough, with the right instruments, at the right times, to detect the signatures that matter. The green glow reported in September adds intrigue. Dicarbon and cyanide compounds can create emerald hues in a cometary coma, but the exact molecular processes driving the observed color remain uncertain. Different telescopes, weather conditions, and observational techniques have yielded varying results, compounding the ambiguity. Here the noir tones of the story emerge. Science corrects, conspiracy connects. The scientific method demands independent confirmations, peer review, and rigorous statistics before it accepts extraordinary claims. Conspiracy thinking requires none of this. It thrives on isolated anomalies, weaving them into compelling narratives that resist conventional verification. 3I Atlas inhabits this liminal space. Its chemistry is surprising but possible. Its timing with Mars is coincidental but captivating. Its invisibility during solar conjunction is astronomically normal but narratively perfect. Too strange to be dismissed as ordinary, too ordinary to be embraced as wholly strange. 3I Atlas sits in ambiguity. Psychologists call this the uncertainty effect, the discomfort and fascination that arise when evidence refuses to resolve neatly. It is this tension, not definitive proof of the extraordinary, that plants the first seed of doubt. Our minds grow more restless when faced with incomplete knowledge. They search for shapes in the clouds, for signals in the static, for patterns in the unknown. 3i Atlas offers exactly that kind of stimulus. It provides just enough anomaly to awaken curiosity, yet remains tethered to the plausible realm of natural explanation. It sits at the boundary, never fully ordinary, never fully extraordinary. As the comet approaches Mars, we are confronted with a peculiar tension. For several weeks during solar conjunction, when Earth's telescopes cannot pierce the glare of the sun, 3i Atlas will be out of sight. Something will happen near the red planet during that absence, though what precisely occurs is hidden from view. By the time contact is restored in late November, the comet may no longer be the same. Comets are transformed by heat. During perihelion passage, solar energy can strip away surface layers, reveal new strata, or trigger the release of volatile compounds long buried in the nucleus. The 3i Atlas that emerges from behind the Sun might present a different chemical fingerprint than the one first recorded in October. Evolution is expected, but the degree of change is unknowable in advance. This uncertainty multiplies. Are we studying a single object, or an evolving sequence of states so distinct they resemble separate bodies? Are the carbon dioxide-rich spectra we measure the signature of the entire nucleus, or simply a fragile crust that will soon give way to deeper reservoirs of water and organics? Will observations after perihelion reinforce the natural comet hypothesis, or suggest that interstellar chemistry can take on forms stranger than our models predict? The possibility remains that clarity will never arrive. 3i Atlas may complete its encounter near Mars, endure its solar heating, and slip away on its hyperbolic path, vanishing into interstellar space. What remains on Earth will be spectral lines, orbital calculations, and a library of conjectures about what transpired during the invisible weeks. Perhaps this is the deeper challenge, not to decide too quickly between natural and artificial, but to sustain scientific discipline while acknowledging the weight of mystery. 3i Atlas becomes more than a comet under these conditions. It becomes a mirror of our readiness to confront anomaly. It tests whether human reason can remain steady when the cosmos refuses to yield certainty, whether we can embrace ambiguity without collapsing into invention or denial. Long before the National Aeronautics and Space Administration aimed its telescopes toward the heavens to seek interstellar visitors, human beings were already studying the night sky with equal parts awe and fear. Ancient astronomers from Sumer, Egypt, the Maya, and China developed intricate systems to track celestial motion. They recorded the rise and fall of planets, calculated eclipses with remarkable accuracy, and mapped the cycles of constellations. Yet they had no conceptual framework for identifying objects that might come from beyond the solar system. The historical record offers no confirmed accounts of anything resembling 3i Atlas, but the silence of those records may reflect limitations of observation rather than absence of such wanderers. Ancient observers concentrated on predictable patterns, the steady march of planets, the reliable return of eclipses, the seasonal reappearance of constellations. A faint and swiftly moving visitor on a hyperbolic path would likely have appeared only as a dim star, drifting briefly across the sky before disappearing into darkness. Still, mythology preserves echoes that some might be tempted to link to such events. With imagination, one can see fragments of astronomical phenomena woven into cultural stories. In Mesopotamia, the Enuma Elish speaks of Marduk arriving from the outer darkness to battle primordial chaos and establish order. Egyptian myth places gods in solar barges, sailing across the cosmic ocean. The Maya tracked Venus with a precision that rivals modern data, yet they also spoke of guest stars, which scholars now interpret as supernovae or comets. Chinese chronicles list unexpected celestial visitors, omens that were believed to signal dynastic change. Such narratives cannot be taken as literal records of interstellar comets, yet they reflect humanity's enduring urge to situate sudden, unusual lights within stories of meaning. There is no evidence linking mythology directly to modern interstellar bodies. What these stories truly reveal is the persistence of pattern-seeking, a cognitive habit as old as humanity itself. 4,000 years ago, as now, the appearance of something extraordinary provoked a search for precedent, for story, for explanation. The same instincts that once warned hunters whether the rustling in the grass signaled predator or wind still shape how we respond to the unknown. When the unknown comes in the form of a green glowing interstellar comet, our brains reach backward as well as outward, grasping for analogies and echoes. Comets, in particular, long functioned as omens. Their sudden arrival in the sky was rarely treated as neutral. When Halley's comet blazed over England in the year 1066, chroniclers interpreted it as heralding the Norman conquest. The Great Comet of 1577 convinced many Europeans that divine judgment was imminent, and nobles saw its path as a sign tied to the Protestant Reformation. In China, elaborate bureaucracies catalogued cometary appearances and correlated them to political transitions, embedding celestial phenomena into the rhythms of dynastic fate. None of these links were causal, but the timing carried immense psychological force. Belief shaped behavior, and behavior in turn made the supposed prophecies appear fulfilled. 3. Atlas enters history at a similarly charged moment. Human civilization stands poised between remaining bound to one world and venturing outward to many. We have detected possible biosignatures in Martian rocks. We have developed the capability to track and even deflect asteroids. We are designing plans for permanent colonies beyond Earth. Against this backdrop, the arrival of an interstellar comet intersects with our emerging self-image as a spacefaring species. The anthropic principle provides one sober lens. We observe events like this now because only now do we have the instruments to perceive them. The universe was not waiting for humanity, but our awareness is naturally synchronized to the moment of our capability, yet timing still unsettles. 3. Atlas does not arrive during just any century of human development. It arrives precisely as scientists study Martian geology for traces of ancient life. Its path does not wander vaguely through the solar system. It crosses the orbit of Mars at the very moment when our exploration of the red planet is reaching a new intensity. Ancient cultures responded to such synchronicities by invoking gods and cosmic will. Modern culture resists that language, yet our explanatory frameworks remain strained when coincidence and meaning seem to overlap so precisely. The comet is natural, its orbit dictated by mathematics indifferent to human history. But it moves across the stage at the exact instant our civilization takes its first steps toward becoming interplanetary. The classical planet Mars, named for the Roman god of war, has always carried a weight of cultural meaning. Its reddish hue became a canvas for human imagination, associated with conflict, upheaval, and transformation. When an interstellar object approaches this planet, something deep within our cultural memory seems to awaken, whether or not we admit it. Mars has never been just a world of rock and dust. It has been a mirror for our own stories of struggle and change. Yet the most intriguing parallel may not be hidden in mythological texts, but in the story of human observation itself. Each generation has developed new tools for looking outward, and with every leap in technology, phenomena once invisible have come into focus. Radio telescopes revealed pulsars, spinning beacons of collapsed stars. Space-based observatories unveiled the existence of planets orbiting other suns. The modern Atlas network now detects interstellar wanderers slipping through our system. The pattern may not be that unusual objects arrive at moments of meaning, but rather that our definition of meaning expands each time our vision sharpens. Perhaps 3.1 Atlas has crossed the inner solar system countless times in ages past. Perhaps comets like it have brushed near Mars for millions of years. But only now do we possess the instruments to dissect its chemistry, to track its hyperbolic path, to situate its presence within the unfolding narrative of Martian exploration. Meaning arises because we can finally see clearly enough to connect the dots. This line of thought inspires a provocative possibility. If advanced civilizations sought to leave traces for emerging species, where might they hide them? The answer could be deceptively simple. In natural phenomena that become legible only when a species has reached sufficient maturity to decode them. Such breadcrumbs would not require machinery or artificial monuments. They could be written into the timing of orbits, the layering of chemistry, the alignments that whisper significance only to eyes trained by physics and astronomy. A comet rich in carbon dioxide appearing when astrobiology stands at the threshold of discovery. Spectroscopic signatures discernible only to instruments capable of infrared precision. Hyperbolic trajectories that become meaningful once orbital mechanics are understood. This, of course, is speculation. There is no evidence that 3i Atlas is anything more than frozen chemistry obeying the laws of motion. Yet, the framework of natural breadcrumbs serves as a thought experiment that helps explain why such events can feel so charged with meaning. Even when analysis insists on coincidence, our instinct searches for connection. The way forward requires a dual approach. We must allow ourselves to explore possibilities while rigorously testing them against data. We must remain open to patterns while acknowledging the human tendency to impose them. We must ask expansive, "what if?" questions while holding to strict, "what is?" standards of evidence. Ancient astronomers who etched planetary motions into clay tablets or mapped cometary paths onto bamboo slips were engaged in the same essential work. Their interpretations were often mistaken, but their observations laid the foundation for everything we know today. Their compulsion to find meaning, however misguided at times, was practice for our own. The difference is that our instruments now reach deeper, our measurements are more exact, our frameworks more disciplined. Yet the underlying impulse has not changed. We still gaze upward, we still feel wonder, and we still try to situate ourselves within an expanse that remains infinite and strange. Occasionally, the universe presents us with phenomena whose timing seems almost scripted, and the old instincts stir again. The sky gods of the past may have been attempts to name realities sensed but not measured. 3i Atlas is precisely the kind of phenomenon that would once have inspired myths of celestial messengers had ancient watchers possessed the telescopes that now reveal it to us. Every few years, the online world rediscovers the myth of Nibiru, the supposed planet on a 3,600-year cycle. According to the story, this hidden world sweeps into the inner solar system on an elongated orbit, bringing with it catastrophe and transformation, ancient astronauts, genetic tampering, and the collapse and rebirth of human civilizations. Its roots lie primarily in the work of Zecharia Sitchin, who interpreted Sumerian cuneiform tablets as evidence that advanced beings called the Anunnaki had once come to Earth in search of gold and left their mark on human evolution. The narrative proved seductive, blurring mythology with speculative science. Yet for decades, the National Aeronautics and Space Administration has dedicated resources to addressing and dismantling the Nibiru claim. No planet of such scale lurks unseen in the outer solar system. If a massive world followed a 3,600-year orbit, its gravitational influence on the planets would be obvious. The precise tracking of planetary motions shows no sign of disturbance. Modern sky surveys, conducted with sensitive instruments across decades, would long ago have revealed an object of that magnitude. The persistence of Nibiru in internet culture illustrates a broader difficulty. When unfalsifiable speculation spreads, it drowns out legitimate mysteries. Ancient astronauts, planetary conspiracies, and imagined cycles crowd the conversation, leaving little room for the careful language of real anomalies. Into this atmosphere of noise enters 3I Atlas, an object profoundly different from fantasy yet often forced into the same conversation. The difference is decisive. 3I Atlas is real. Its light has been measured, its coma observed, its orbit calculated. Independent observatories across the globe have confirmed its path. Its hyperbolic trajectory is not speculation but mathematics. Instruments as sophisticated as the James Webb Space Telescope have examined its chemistry, detecting the unusual dominance of carbon dioxide over water. Unlike the cyclical myth of Nibiru, this comet does not return on a timetable. Hyperbolic orbits are one-way passages. An interstellar traveler arrives, cuts across the solar system, and departs again into the dark, never to repeat its journey. Still, the endurance of cyclical myths reveals something essential about the human imagination. People seek patterns, even when those patterns are inventions. The notion that cosmic events repeat on predictable scales provides comfort, suggesting control over forces otherwise unfathomable. If the return of gods or planets can be calculated, then preparations can be made. Predictability, even in myth, becomes a shield against the vast uncertainty of space. Interstellar visitors offer no such comfort. They emerge from random directions without warning, following orbits determined not by prophecy, but by the impartial mechanics of gravity. They leave just as suddenly, beyond the reach of preparation or prediction. Their unpredictability unsettles, for it strips away the illusion of cosmic order. At least those who believe in Nibiru know what to expect and when to expect it. A body like 3I Atlas offers only the unknown, chemistry that seems tailored to planetary atmospheres, timing that places it close to Mars, and a trajectory that vanishes into interstellar night. This contrast underscores why critical thinking matters in moments of wonder. Science advances by acknowledging ignorance, testing hypotheses, and revising its conclusions as new evidence arrives. Pseudoscience, by contrast, insists on certainty, resists testing, and treats every observation as proof of a predetermined belief. Yet the attraction of cyclical myths should not be dismissed entirely. They reveal a psychological need to impose order on chaos, to create meaning where the universe seems indifferent. The universe is ancient, immense, and filled with phenomena that defy simple comprehension. The urge to weave cycles into its workings is a human response to existential uncertainty. Perhaps that impulse, properly harnessed, can be redirected toward genuine discovery. Instead of fictional timelines, attention could turn to real data. In less than a decade, astronomers have identified 3 confirmed interstellar visitors. The first, 1I Oumuamua, carried the riddle of unexplained acceleration. The second, 2I Borisov, behaved like a textbook comet. The third, 3I Atlas, brings chemistry rich in carbon dioxide and an approach that coincides with renewed focus on Mars. Each of these objects is unique, none bound by mythical cycles, and together they hint at a reality stranger than folklore, that the galaxy may deliver such messengers far more frequently than once imagined. That amount of data is far too small for any true statistical analysis, yet it already hints that interstellar space may be more chemically varied than our existing models have predicted. The real cycle of roughly 3,600 years is not the imagined return of ancient astronauts, but rather the span of time during which human civilization has kept written records detailed enough to trace celestial patterns. For approximately that long, humanity has looked to the sky with systematic attention, refining ever more sophisticated instruments to measure what once seemed unknowable. If there is a meaningful cycle, perhaps it is not cosmic but technological. Every few generations, human ingenuity expands the reach of our senses. Each advance reveals classes of phenomena that were always there, waiting to be noticed. Radio astronomy opened the door to pulsars, quasars, and the cosmic microwave background. Space-based detectors unveiled gamma-ray bursts, gravitational waves, and thousands of exoplanets. Automated sky surveys now sweep the heavens with precision, cataloging asteroids, supernovae, and the occasional wanderer from another star. 3.1 Atlas represents the newest chapter of this unfolding story. For the first time, humanity can not only detect and track such interstellar visitors, but also probe their chemical makeup. This capability is scarcely a decade old, which means our sense of what is typical or extraordinary for these travelers is still forming. What seems anomalous today may, in the coming years, prove to be commonplace. The internet magnifies both the promise and the peril of this accelerated discovery. Authentic astronomical findings spread worldwide in hours, allowing near-instant collaboration and verification across borders. At the same time, misinformation races just as swiftly, blending authentic mysteries with theories of ancient astronauts and planetary conspiracies. The true challenge is to preserve scientific discipline while admitting the incompleteness of our knowledge. Interstellar chemistry and orbital mechanics may hold surprises, but surprise does not automatically demand extraordinary explanations. Sometimes nature is more inventive than the categories we have built to contain it. It is reasonable to ask whether ancient myths might carry distorted echoes of genuine celestial events. Comets blazing across the night, meteor showers streaking through the sky, or the shimmering curtains of aurora would all have appeared supernatural to observers in pre-industrial societies. Yet, acknowledging that the heavens-inspired mythology differs from claiming that mythology accurately records astronomy. The Sumerian tablets that Zechariah Sitchin translated contain profound achievements in mathematics, astronomy, and engineering. They reflect the cosmological frameworks of their own age, not hidden transmissions from extraterrestrial teachers. When modern readers overlay contemporary science onto ancient writings, they often uncover more about current cultural desires than about the past itself. 3. Atlas gives us the opportunity to practice a kind of intellectual hygiene. Its oddities can be recognized without invoking theories of deliberate intervention. Its potential implications for Martian atmospheric chemistry can be studied without claims of intentional terraforming. Its timing can be noted without discarding the standards of evidence that distinguish science from speculation. The real cycle worthy of attention is not the mythical return of Nibiru, but the recurrent human impulse to seek meaning in cosmic events, matched by our expanding capacity to test those meanings against observation. As 3i Atlas moves into its hidden passage near Mars, humanity participates once again in its oldest intellectual tradition, watching the heavens, searching for patterns, and measuring our place within a universe that constantly presents phenomena that unsettle the boundaries of expectation. Let us return to the chemistry that makes 3i Atlas so compelling, a ratio of carbon dioxide to water of approximately 8:1, among the highest ever measured in any comet. This single figure opens a window into speculation, because it resonates not only with theories of comet formation but also with the long history of Mars. To appreciate its significance, one must think of Mars not merely as the cold desert we see today, but as it once was, and as it might one day become again. Around 4 billion years ago, Mars was cloaked in a dense atmosphere. Rivers wound across its surface, deltas formed at the edges of ancient lakes, and minerals requiring liquid water crystallized in its rocks. The surface we see now bears the unmistakable scars of erosion. River valleys carved deep into the crust, the traces of floodplains, and deposits that only flowing water could have left behind. Jezero Crater, where the Perseverance rover searches for traces of ancient biology, is itself the remnant of a wetter, more habitable Mars. The decline from that era to today is stark. Mars lost its magnetic field early in its history, leaving the atmosphere exposed to relentless solar wind stripping. Over billions of years, what was once a thick protective blanket thinned to less than 1% of Earth's surface pressure. What remains is composed mostly of carbon dioxide, around 95%, but in a quantity far too small to trap enough heat or create the pressure necessary for liquid water to persist on the surface. In theory, if the atmosphere could somehow be thickened while maintaining its carbon dioxide composition, Mars might regain some of its former warmth and stability. It is at this point that 3I Atlas re-enters the picture, carrying a coma dominated by the very gas that Mars needs most. The James Webb Space Telescope and the Sphere-X mission have both confirmed this unusual chemistry. Carbon dioxide in overwhelming abundance, alongside carbon monoxide, carbonyl sulfide, and buried layers of water ice. Together, they form what looks very much like a cosmic chemistry kit designed for atmospheric modification. Scale, however, is everything. A single comet cannot change the fate of a planet. Mars has been bleeding gases into space for billions of years. To compare, even if 3I Atlas were to deposit its entire supply of volatile materials into the Martian sky, the effect would be minuscule, like sprinkling a teaspoon of sugar into an empty Olympic swimming pool. The numbers make clear that one comet is insufficient, yet the imagination is tempted to frame the event differently. What if 3I Atlas is not the whole story, but one episode in a longer sequence? If the goal were gradual atmospheric restoration over immense spans of time, then repeated deliveries of carbon dioxide, rich material, would be precisely the right mechanism. Heating patterns reinforce this speculation. As 3I Atlas approaches perihelion at the end of October, solar energy will trigger the most vigorous outgassing of its journey, precisely when its orbit brings it closest to Mars. The geometry aligns in striking fashion, the moment of maximum chemical release coinciding with the planet that stands to benefit most from such chemistry. Recent spectroscopic data has deepened the puzzle, revealing organic compounds that could seed more complex reactions within a planetary atmosphere. The detection of carbon monoxide suggests formation conditions unlike those typical of solar system comets. A further reminder that 3I Atlas originates from a different stellar nursery. Then there is the glow. In September, astronomers reported a distinct green tint to the coma, a hue often associated with cyanide compounds or dicarbon molecules. Either could play a role in complex atmospheric processes. Even if the glow arises purely from natural sublimation, it adds to the sense that this object carries with it the kind of chemistry that planetary engineers would prize. And yet caution is essential. It is easy, when confronted with such neat coincidences, to project design onto nature. Comets outgas because they are heated, and they release what they contain. The fact that 3I Atlas expels carbon dioxide in abundance does not mean that it was programmed to deliver it. It is more likely a reflection of its birthplace, a region of its home system cold enough for carbon dioxide to freeze while water remained in vapor form. Another possibility is selective sublimation. If the surface of the nucleus is coated with carbon dioxide ice, This outer layer could shield deeper deposits of water ice, skewing the chemical signature until the sun's warmth digs deeper. As the comet continues to approach its closest point to the sun, these ratios may evolve, exposing new strata of frozen history. The timing of its most intense activity happens to coincide with a period of observational blindness. When 3I Atlas passes closest to Mars, it will also be hidden from Earth's instruments, passing behind the Sun during solar conjunction. For several weeks, even the most advanced telescopes will be unable to monitor it. This creates a natural gap in our ability to observe at the exact moment when the comet's chemistry is at its most expressive. If this were a scene from speculative fiction, the arrangement would seem too perfect. An interstellar courier timed to release atmospheric ingredients at Mars precisely when Earth cannot watch. The chemistry appears tuned, the geometry aligned, the concealment guaranteed. But the real universe follows the laws of physics rather than the arcs of storytelling. The invisibility is not evidence of a hidden agenda, but the ordinary consequence of orbital mechanics. 3I Atlas offers a reminder of both wonder and restraint. It is extraordinary enough to witness an interstellar object with such unusual chemistry brushing past Mars at the very moment we are probing the planet for signs of life. To imagine more is tempting, but the true narrative lies in the interplay of natural processes, frozen chemistry, solar heating, gravitational geometry, operating on scales vast enough to unsettle, yet precise enough to explain. The release of carbon dioxide from 3I Atlas reflects the nuclear composition locked into the comet at the time of its formation around a distant star, not the outcome of any atmospheric engineering blueprint. Still, the sequence of coincidences unfolds with an almost satirical precision. An interstellar visitor rich in greenhouse gases appears in the solar system at the very moment scientists announce potential biosignatures in Martian rocks. Its chemistry is dominated by precisely the compounds Mars would need if its atmosphere were ever to be thickened and warmed. Its trajectory ensures that maximum solar heating, and therefore maximum outgassing, occurs during its closest approach to Mars, while Earth itself remains unable to observe due to solar conjunction. During this crucial interval, instruments already orbiting Mars may provide the only evidence of what actually occurs. The European Space Agency's Trace Gas Orbiter is designed to identify and quantify atmospheric constituents. If 3I Atlas were to release significant volumes of carbon dioxide or associated volatiles in the Martian environment, the orbiter could detect and analyze the signatures. Mars Express, still active after nearly 2 decades, might even capture images of the comet's coma structure as it passes nearby. These spacecraft offer the best chance of distinguishing coincidence from contribution. The criteria for identifying intentional atmospheric engineering, however, are subtle. Astronomers would look for gas jets focused unnaturally toward Mars, chemical signatures that vary depending on planetary proximity, or outgassing patterns inconsistent with solar heating. None of these indicators have yet been observed. Still, the decisive measurements will take place during Earth's enforced period of blindness, when only Mars-based instruments can continue the watch. Speculation about terraforming may stretch scientific credibility, yet it serves a valuable purpose. It frames Mars not as a frozen museum of ancient history, but as a dynamic world that could, in principle, be reshaped by external inputs. Whether those inputs originate from interstellar delivery or from human technological intervention, the chemistry remains fundamentally the same. Carbon dioxide for greenhouse warming, water vapor for hydrological cycles, and trace organic molecules for chemical complexity all represent the essential building blocks of atmospheric restoration. In this light, 3I Atlas acts as a kind of demonstration model. Its coma is a mixture perfectly aligned with what planetary engineers would design: greenhouse gases to trap heat, water to sustain surface processes, and organic precursors to encourage more complex reactions. The scale is modest, far too small to produce dramatic change on Mars. But scale is not the only lesson. As October approaches, the value of the encounter lies in what can be learned about chemistry, delivery mechanisms, and the availability of interstellar materials. The real act of terraforming may not be happening on Mars at all, but within human imagination, as this comet forces us to envision the red planet not solely as it is today, but as it might one day become. The scientific baseline must be set out with clarity. At present, there is no evidence that 3.1 Atlas carries living organisms or biological material. Interstellar space is among the harshest environments imaginable, a realm of cosmic radiation, freezing cold, and deep vacuum that would destroy most biological molecules long before they could survive the millions of years required for travel between stars. Yet the lack of evidence does not eliminate the space for speculation. Among the most provocative hypotheses in astrobiology is directed panspermia, the idea that life might spread across the galaxy not by accident, but through deliberate seeding. If an advanced civilization wished to distribute biological material across interstellar distances, comets would make ideal couriers. They are durable, chemically rich, and naturally suited for long journeys. The chemistry, already confirmed in 3.1 Atlas, makes this thought experiment compelling. Carbon dioxide, water, and organic compounds form precisely the molecular foundation required for carbon-based life. These elements can support biology, but they are not life themselves. The distinction is critical. Possessing the ingredients for a cake does not mean the cake exists. Still, the timing of this comet's arrival cannot help but capture attention. Just as potential biosignatures are reported in Martian rocks, an interstellar visitor appears bearing the raw chemical toolkit that could enable atmospheric restoration and biological complexity. The coincidence feels crafted by narrative, if not by intention. Ideas about dormant potential are not limited to comets. Molecular biology once treated large portions of the genome as junk DNA, meaningless leftovers. Modern science has shown that many of these regions contain vital regulatory sequences and evolutionary records. They are not empty, but rather hold functions awaiting the right conditions for expression. There is no evidence of a hidden cosmic code embedded in Martian geology, waiting to be activated by interstellar chemistry. Yet, as a metaphor, it is powerful. Mars itself may contain switches, ancient biological remnants preserved in mudstones or subsurface deposits that could respond to improved atmospheric conditions. The potential biosignatures in Jezero crater are already reminders that Mars once had what was necessary for life. Whether any fragment of that biology remains dormant is unknown. Speculation aside, the most immediate activation is not Martian biology but human behavior. The reports of possible biosignatures have energized the field of astrobiology, drawing funding, political support, and renewed attention to Mars exploration. Sample return missions, long debated and delayed, have gained urgency. 3.1 Atlas, with its peculiar chemistry and timely passage, amplifies this momentum by adding drama and narrative weight. The comet may not activate Martian biology, but it has already activated human imagination, reshaping the way we see Mars and our place in the cosmos. The panspermia hypothesis has a long history. First suggested by Svante Arrhenius in the year 1906, it proposed that life might be dispersed by comets, meteoroids, or interstellar dust. Most scientists consider natural panspermia unlikely, given the destructive conditions of space. But directed panspermia, intentional seeding by an advanced intelligence, remains theoretically possible. If 3I Atlas were in fact carrying biological material, what would we expect to find? Perhaps organic molecules more complex than simple hydrocarbons. Perhaps chemical patterns resembling metabolism. Perhaps isotopic ratios skewed in ways that distinguish biology from geology. In the most dramatic case, perhaps even preserved cellular structures capable of surviving the journey. So far, none of this has been observed. Spectroscopic instruments have indeed detected organic compounds in the coma of 3I Atlas, but these appear to be simple molecules consistent with known natural processes. Nothing suggests biological origin, yet remote sensing has limits, and subtler signals could remain hidden from our instruments. The true test would come from direct sampling. That will not happen with this visitor. The European Space Agency has confirmed that no intercept mission is feasible. Future interstellar bodies, however, might present the chance for physical collection and laboratory analysis. Meanwhile, Mars itself holds the most promising near-term opportunity. The Perseverance rover continues to search Jezero crater, where leopard spot textures in mudstones may contain fossilized biosignatures. The Mars Sample Return mission, though delayed, still aims for the early decades of the 21st century. Those rocks could reveal preserved organic molecules, isotopic clues, or even structural evidence of past microbial life. If Mars once hosted biology, and if remnants of genetic material persist, then a thickened atmosphere could, in principle, revive some dormant processes. This remains highly speculative, but it is not inconceivable. On Earth, microorganisms have been revived from subsurface environments after millions of years of stasis. The link between interstellar chemistry and planetary biology may be subtle rather than direct. Molecules formed around distant stars could seed prebiotic chemistry on young worlds. Carbon dioxide, methane, and water, all identified in 3I Atlas, are fundamental raw materials for chemical evolution. These building blocks are not rare. They are scattered across interstellar space in enormous quantities. What makes 3I Atlas notable is not that it carries them, but that it carries them here, at this moment, close enough for us to observe. The danger lies in interpreting coincidences as evidence of design. The universe is saturated with organic chemistry. Comets, asteroids, and molecular clouds all contribute to the vast reservoir of life's ingredients. The appearance of those ingredients in 3I Atlas is striking, but it is part of a larger story in which the galaxy continually produces and disperses the raw material of biology. The arrival of comets rich in carbon compounds at worlds with potential habitability is likely more common than rare. What distinguishes 3I Atlas is not simply that it carries organic chemistry, but that it appears at precisely the moment when humanity is most attuned to questions about Mars and its possible biological past. In this sense, the comet operates as a kind of cosmic Rorschach test, a mirror that reflects human hopes and anxieties about life elsewhere in the universe. The attraction of linking its chemistry to biology tells us as much about ourselves as it does about the comet. Human beings are pattern-seeking organisms, evolved to perceive relationships in complex and uncertain environments. When confronted with phenomena like 3I Atlas, with its unusual chemistry arriving at a moment of heightened interest in Martian biosignatures, our instinct is to connect the dots. This biological programming activates regardless of whether the connections are real. The same capacity that allows scientists to identify subtle signs of life also carries the danger of imposing narratives on what might be only chemical or physical events. A practical test for biological relevance lies in spectroscopy. If amino acids, nucleotides, or other complex organic molecules were present in sufficient abundance within the coma of 3I Atlas, current instrumentation could in principle detect them. The Mars orbiters already in place provide a unique opportunity. During the October passage, the Trace Gas Orbiter, designed specifically to examine atmospheric chemistry, could search for signs of biological complexity. Mars Express, with its imaging capabilities, might capture structural details of the comet's coma that hint at unusual activity. These spacecraft represent the best tools available to explore the question of whether 3I Atlas carries anything beyond the expected suite of simple organics. Regardless of the outcome, the comet's presence has already produced an undeniable shift in human consciousness. It reminds us that we live in a universe where interstellar chemistry intersects with planetary environments in ways that challenge our imagination. The significance lies not in the likelihood of Mars being seeded with life by this visitor, but in the way its arrival stimulates curiosity, investment, and renewed determination to pursue astrobiology. The story of 3I Atlas may ultimately be less about what the comet contains and more about what it compels us to seek. Step away from the telescopes for a moment and consider how stories shape human behavior on scales ranging from the intimate to the civilizational. The narratives we craft about cosmic events do more than mirror our understanding of the universe. They guide how we respond to new information, how resources are allocated, and how decisions about humanity's future are made. The history of comet interpretation illustrates this feedback loop with particular clarity. Halley's Comet, returning every 76 years, has inspired centuries of wildly different responses depending on the cultural framework of the time. To medieval Europeans, its arrival signaled plague, war, and political instability. To Renaissance astronomers, it was proof of celestial regularity, confirmation that the heavens followed natural law. To modern observers, Halley's Comet represents a research opportunity, a predictable visitor that can be probed by spacecraft and ground-based observatories alike. The comet has not changed, but the stories surrounding it have, and the consequences of those stories are visible in human history. 3I Atlas enters at a moment when our stories about cosmic visitors are themselves in flux. In the year 2022, the DART mission demonstrated that humanity could deliberately alter the trajectory of a celestial body. With that impact test, humanity graduated from passive spectators to active participants in solar system dynamics. This technological leap inevitably shifts how we interpret interstellar wanderers. They are no longer just curiosities or omens, but potential resources, possible hazards, and perhaps even subjects for future engineering. Media ecosystems amplify this transformation in ways no previous generation has experienced. Social platforms reward spectacle and emotional intensity, spreading dramatic claims with viral speed. A suggestion that 3I Atlas is an alien construct can reach millions overnight, while carefully written scientific analyses of its volatile chemistry remain locked in journals read by only hundreds. The result is a dangerous distortion. Speculation multiplies more quickly than verification, drowning out careful uncertainty with the noise of manufactured certainty. The balance between discovery and distortion grows ever more precarious. Behind the headlines, planetary defense infrastructure quietly performs miracles of surveillance. The Atlas Telescope Network, PanSTARRS, and similar systems sweep across the night sky every few days, automatically identifying and tracking objects that might pose danger. This capability has reduced the likelihood of being caught unaware by a rogue asteroid, but it has also changed public consciousness. Now we live in an age when interstellar objects are identified and announced within days of discovery, complete with preliminary orbital elements, chemical signatures, and risk assessments. The speed of this information flow enables scientific collaboration on a global scale, but it also leaves room for premature speculation, misunderstanding, and anxiety. 3I. Atlas refuses to sit comfortably in existing categories. Its chemistry is highly unusual. Its trajectory places it near Mars during a period of maximum solar heating, and its closest approach will occur during weeks when Earth cannot observe directly. These uncertainties fuel legitimate inquiry, but they also invite less disciplined forms of speculation. The difference between constructive curiosity and destructive rumor depends on how well we tell the story. Education plays a crucial role here. How students are taught to approach cosmic mysteries, how to weigh evidence, tolerate ambiguity, and distinguish between hypothesis and fantasy will determine whether the next generation meets objects like 3I Atlas with curiosity rooted in science or credulity driven by myth. The goal is not to suppress speculation, but to channel it into questions that can be tested, measured, and refined. The economic dimension is equally significant. Public willingness to support asteroid detection, Mars missions, and interstellar research is shaped by the stories that make those efforts feel urgent. A narrative that frames 3I Atlas as both scientifically mysterious and practically relevant can strengthen support for the infrastructure that keeps Earth safe and expands our knowledge. Yet storytelling carries risk. Emphasize the dramatic too heavily, and reality may disappoint. If 3I Atlas proves to be a conventional comet with slightly unconventional chemistry, will public attention fade? The comet itself will come and go, but the stories we build around it will continue to influence science, culture, and policy long after its green glow has vanished into interstellar night. Will public support for astronomical surveillance decline if the mystery of 3I Atlas collapses into a mundane explanation? That question hovers around every cosmic anomaly. The best safeguard is not in clinging to sensational stories, but in cultivating a healthy toolkit for interpretation, one that combines source verification, statistical literacy, predictive testing, and tolerance for uncertainty. Source verification is the first line of defense. Not all claims about 3I Atlas deserve equal weight. A peer-reviewed paper that has survived rigorous scrutiny holds more authority than a viral social media post. Institutional statements from the National Aeronautics and Space Administration or the European Space Agency deserve more confidence than anonymous speculation on internet forums. A hierarchy of credibility is not elitism, but a necessary framework for distinguishing between signal and noise. Statistical literacy provides the next layer. 3I Atlas is unusual among the 3 confirmed interstellar visitors we have observed, but 3 objects do not constitute a meaningful dataset. The singularity of its chemistry may prove less unique as our instruments improve and more interstellar wanderers are catalogued. What feels anomalous in a dataset of 3 may become typical in a dataset of 30. Recognizing the limits of sample size prevents us from over-interpreting rare events. Predictive testing is another safeguard. Useful theories make testable predictions about behavior that can be checked against future observations. If a hypothesis about 3I Atlas specifies what its outgassing should look like during the October encounter with Mars, then the theory can be evaluated. Ideas that remain unfalsifiable, immune to evidence regardless of what is observed, contribute little to genuine understanding. Uncertainty tolerance may be the most essential skill of all. The universe routinely delivers puzzles that strain our frameworks without necessarily requiring extraordinary explanations. 3I Atlas is puzzling in ways that may remain unresolved with current technology. Accepting that incompleteness is not defeat, but a necessary part of science. The way information circulates also shapes perception. Algorithm-driven platforms privilege engagement over accuracy, rewarding dramatic claims about alien artifacts while burying sober analyses of spectroscopic data. Recognizing these systemic biases helps us evaluate why certain narratives dominate public discourse. Visual communication compounds the effect. Presenting 3-1 atlas with actual data produces one kind of understanding, while rendering it in sensational concept art produces another. Side by side, the comparison illustrates how aesthetics influence interpretation. As the October encounter approaches, these narrative dynamics grow sharper. 3I Atlas may confirm our hypothesis of a natural comet, reveal something anomalous, or most likely, expand the data without fully resolving the mystery. Whatever the outcome, the way we tell the story will affect support for space exploration, planetary defense initiatives, and funding for interstellar research. The influence of stories about cosmic visitors reaches beyond immediate policy. They shape our collective sense of humanity's place in the cosmos, our responsibilities as a species with expanding reach, and our readiness to face phenomena that defy easy categorization. In the end, 3I Atlas may be less a test of interstellar chemistry than a test of how human consciousness responds to ambiguity, whether we can sustain curiosity without rushing to closure. Here is a speculative twist that reframes the puzzle of 3I Atlas without invoking extraterrestrial engineers. What if the beings responsible for atmospheric projects were not aliens at all, but us, an earlier version of human civilization that once reached technological maturity, only to collapse and vanish, leaving behind automated systems still functioning across cosmic timescales? Such a hypothesis requires an audacious stretch of imagination. It demands that human civilization, or something very much like it, achieved interstellar capability hundreds of thousands or even millions of years ago. Then came catastrophe, ecological ruin, war, or cosmic disaster that erased nearly every trace of that achievement from the geological record. Before their fall, this ancestral civilization might have deployed self-replicating systems designed to maintain habitable conditions on promising worlds. Comets, durable and mobile, could serve as the couriers of such systems, carrying payloads tailored for greenhouse warming, atmospheric thickening, and prebiotic chemistry. What evidence would support the existence of such a predecessor? One might expect to find industrial byproducts in ancient ice cores or sedimentary layers, chemical scars that natural geology cannot easily explain. There might be isotopic anomalies consistent with nuclear technologies, artificial materials, or structures preserved on the Moon, where erosion is minimal, or orbital debris lingering in stable paths around Earth. Even genetic signatures in terrestrial organisms could raise questions, alterations that natural selection alone could not easily account for. To date, none of these indicators have been confirmed, but the absence of evidence does not necessarily preclude the possibility. It constrains the scale and longevity of any hypothetical ancient civilization. Mars would have been an obvious target for such efforts. The planet lies within the habitable zone, contains water-bearing minerals, and once sustained a thick atmosphere and flowing rivers. A technologically advanced humanity of deep antiquity might have seen Mars as a candidate for atmospheric renewal and deployed automated systems to act over millions of years. In this light, 3I Atlas could be more than a comet. It could be an engineered delivery system, carrying the very gases Mars needs most at precisely the moment when a surviving humanity has regained enough capability to recognize and potentially assist the process. The observed chemistry aligns with this speculation. A carbon dioxide to water ratio of roughly 8:1 is not only unusual, but also precisely suited for Martian greenhouse warming. trace organic compounds add complexity. The timing of maximum outgassing during closest approach to Mars could be interpreted as deliberate targeting rather than coincidence. From this perspective, the comet appears optimized, almost scripted, for atmospheric engineering. Yet the challenges are immense. Directing comets across interstellar space with such precision would require mastery of gravitational dynamics, far beyond our current abilities. Even an advanced civilization would struggle to program trajectories over millions of years with reliable accuracy. Moreover, engineered objects tend to betray their artificiality. One would expect structured radio emissions, geometric design, evidence of propulsion, or chemical compositions that defy natural processes. None of these have been observed in 3I Atlas. What remains is a story, a speculation about continuity and loss, about human potential extended across epochs and then forgotten. Whether or not such a civilization ever existed, the idea illustrates how 3I Atlas forces us to look both outward and inward toward the chemistry of interstellar comets and toward the hidden possibilities of our own past. 3I Atlas displays none of the conventional signatures of engineering. There are no narrowband radio emissions, no geometric structures, no anomalous accelerations that would imply propulsion. To all of our instruments, it looks like a comet strange in chemistry, unusual in timing, but still consistent with natural processes. Yet the hypothesis that it might be part of an engineered system remains worth considering, not because the evidence demands it, but because it offers a framework for addressing the coincidence of chemistry and timing without leaping immediately to external alien intelligence. The speculative twist is this: what if the engineers were not extraterrestrials at all, but humans or human-like beings that reached technological maturity in the distant past? If such a civilization existed, Mars would have been their logical first target for atmospheric engineering. It lies within the habitable zone, contains the geological foundations necessary for sustaining life, and once possessed the thick atmosphere and surface water that could support biological complexity. The convergence we now witness, the detection of potential biosignatures in Martian rocks, alongside the arrival of an interstellar comet rich in greenhouse gases, could represent the intended coordination of ancient systems set in motion long before our own civilization emerged. This possibility also explains why 3I Atlas appears natural while carrying properties that feel almost too convenient. Advanced atmospheric engineering might be designed to camouflage itself, appearing indistinguishable from natural phenomena until a civilization becomes technologically sophisticated enough to recognize the pattern. Such concealment could serve a pedagogical function, forcing developing species to earn their awareness by advancing their observational capabilities. In this interpretation, 3I Atlas becomes a kind of cosmic examination, a test of whether we are mature enough as a civilization to recognize and respond to atmospheric assistance when it arrives. The falsifiability of the hypothesis is its greatest strength and its greatest weakness. In principle, we could test it by searching for engineered signatures that our current instruments might have missed: narrowband emissions, structured variations in reflected light, or chemical changes that correlate with planetary proximity. The European Space Agency's orbiters around Mars provide the best opportunity for such observations during the October encounter. If 3I Atlas is engineered, its closest approach could reveal targeted gas release or other behaviors inconsistent with solar heating alone. But even if evidence of engineering emerged, attributing it to earlier humans would remain speculative. The galaxy has had billions of years to produce civilizations capable of interstellar projects, Atmospheric engineering could have been developed by any advanced species that reached technological maturity before us. The psychological appeal of the earlier humans hypothesis lies in its anthropocentrism. It allows us to imagine that the technology is recognizably ours, not alien in form or purpose. Discovering our own forgotten legacy feels more comfortable than confronting truly foreign intelligence. That comfort does not make the hypothesis more probable, but it explains its resonance. The timeline required for such a scenario would be immense. A civilization would need to rise, achieve interstellar engineering, deploy systems designed to function autonomously across millions of years, and then collapse so thoroughly that almost no trace remains. Earth's geological record currently shows no sign of industrial activity before the present human era. Still, traces of space-based civilizations would be less likely to survive in sediments or ice cores. Artificial structures on the moon, orbital debris, or isotopic anomalies from advanced energy use could provide evidence, but so far, none has been confirmed. Another variation imagines Mars itself as the cradle of such a civilization. During its more habitable epoch, intelligent life might have arisen there, achieved interstellar capability, and then fallen when the atmosphere collapsed. In that scenario, long-term restoration systems could have been set in place to prepare the planet for eventual rehabilitation. This would explain why 3I Atlas seems so perfectly suited to Mars, carrying carbon dioxide in overwhelming abundance and releasing it at the optimal moment of closest approach. Automated systems could even be programmed to intensify activity once signs of renewed biological interest appear, such as the arrival of spacefaring neighbors. The engineering challenges, however, are formidable. Programming interstellar comets to deliver precise chemical payloads at specific locations across cosmic timescales would require mastery of gravitational dynamics and trajectory corrections far beyond our current imagination. Preserving volatile chemistry over millions of years, while ensuring activation during planetary proximity, adds layers of complexity almost beyond comprehension. These obstacles make the idea difficult to accept as anything more than speculation. Yet the alternative that all of this is coincidence strains credibility in its own way. The odds of an interstellar comet arriving with exactly the right chemical balance for Martian atmospheric restoration, at exactly the moment we discover potential biosignatures in Martian rocks, feel vanishingly small. Perhaps the real challenge is not determining whether 3I Atlas is engineered, but learning how to recognize engineering that is so advanced it appears natural. This line of speculation positions the hypothesis of earlier humans, or human-like beings, as a middle ground between pure coincidence and alien intervention. It allows for the possibility of technology without abandoning the psychological comfort of continuity. It also reframes the comet as more than frozen chemistry. It becomes a mirror, reflecting human potential across unimaginable spans of time. If such a civilization once existed, 3I Atlas would represent both gift and reminder, a delivery of atmospheric ingredients that could help restore Mars, and a warning that civilizations capable of such feats are also vulnerable to collapse. In this sense, the comet carries not just carbon dioxide, water, and organic compounds, but also a narrative about survival, legacy, and responsibility. As 3I Atlas approaches its concealed encounter with Mars, humanity finds itself at the intersection of observation and imagination. The instruments we point at the sky may reveal nothing more than natural chemistry, but the story we build around that chemistry may reveal much more about us, our readiness to face uncertainty, our appetite for continuity with the past, and our willingness to accept the responsibilities of technological maturity. The comet becomes a participant in our cultural imagination, challenging us to consider what it means to inherit not just a planet, but a cosmic history. If our predecessors truly seeded the galaxy with atmospheric engineering systems, then 3I Atlas is not only a delivery vehicle, but a message in motion, reminding us that civilizations rise, fall, and rise again across spans of time, far greater than any single life or epoch. In this way, the mystery of 3I Atlas points beyond chemistry and coincidence, pressing us to confront the possibility that we are part of a story older and larger than we have yet imagined. Imagine, for a moment, vast computational networks buried beneath the world's great deserts, quantum processing systems designed not for trivial tasks but for the most consequential of all, modeling civilizational collapse, predicting the timing of optimal intervention, and coordinating planetary restoration projects across galactic distances. This remains the province of science fiction, yet as a metaphor it proves useful. It suggests how truly advanced civilizations might confront the challenge of long-term survival on scales far beyond any individual lifetime. The speculative concept of quantum archaeology proposes that powerful computers could reconstruct historical events from faint physical traces, residues in quantum fields, subatomic interactions, and information, theoretic imprints left in matter itself. While no such technology exists today, the underlying notion that the universe retains information about past events finds echoes in theoretical physics. If such capabilities were real, then an advanced civilization facing collapse might deploy these systems to determine precisely when and how to assist with species recovery. Buried networks of unimaginable complexity could, in theory, monitor planetary conditions, track the progress of technological development, and activate delivery systems only when emerging civilizations had reached the maturity required to benefit from atmospheric restoration. Within this speculative framework, 3I Atlas would not be a coincidental visitor, but the product of predictive algorithms operating across cosmic timescales. Its arrival aligns with human discovery of potential Martian biosignatures, the development of interplanetary exploration, and growing debates about planetary-scale climate engineering. The comet becomes, in this scenario, an engineered messenger arriving not too soon, not too late, but at exactly the moment when its symbolism and chemistry could most influence a civilization on the verge of wider awareness. Such speculation remains firmly within the realm of narrative imagination. No evidence points to hidden desert supercomputers, nor to predictive algorithms stretching across millions of years. Yet the metaphor helps us grapple with the scale of planning required by civilizations more advanced than ours. The reality of modern computational networks already hints at this direction. The Atlas telescope system, which first detected 3I Atlas, operates through automated sky surveys that scan the heavens continuously, feeding enormous data streams into software that identifies anomalies. Human operators are alerted only after algorithms have performed the first layer of analysis. International institutions now run models that predict asteroid trajectories, calculate impact risks, and even simulate potential deflection strategies. The success of the DART mission in 2022 proved that humankind has graduated from passive observation to active participation in celestial mechanics. We have begun to change orbits intentionally, albeit on small scales. Interstellar atmospheric engineering, however, would demand orders of magnitude more computational power, predictive accuracy, and technological sophistication. Deserts provide a striking metaphor for preservation. They already safeguard natural and human artifacts with extraordinary fidelity. Meteorites lie unchanged for millions of years. Ancient settlements remain preserved beneath sand. Geological layers reveal histories stretching back deep into time. If someone wished to hide computational systems for epochs, deserts would be an ideal choice. Their arid stability, minimal biological activity, and relative geological quiet could shield machinery from decay. While ground-penetrating radar and modern surveys have uncovered no such hidden structures, the absence of detection cannot wholly rule out the possibility of carefully concealed networks designed to activate only under specific conditions. The desert supercomputer metaphor illuminates the kind of foresight needed for planetary restoration. Mars lost its atmosphere not in a single cataclysm, but through slow attrition solar wind stripping away gases once protected by a magnetic field, interactions between geology and atmosphere, bleeding pressure over billions of years. Reversing such a process would require interventions that operate across equally vast timescales. No single comet, not even one as chemically rich as 3I Atlas, could thicken the Martian atmosphere by itself. Yet repeated deliveries of volatile material over millions of years might gradually shift the balance, nudging the planet toward renewed habitability. The James Webb Space Telescope stands today as the pinnacle of our observational reach, capturing data that reveals the chemistry of interstellar objects and exoplanetary atmospheres alike. From its golden mirrors, we glimpse only fragments of what more advanced civilizations might know. Where we see an anomaly in the chemistry of a passing comet, others with deeper tools might perceive the deliberate strokes of a design painted across cosmic time. A quantum leap in our capacity to analyze the chemistry of distant objects has already transformed astronomy. The James Webb Space Telescope can now read what might be called the spectral fossils of ancient processes, signatures of chemical reactions that occurred around other stars millions of years ago. Interstellar visitors such as 3I Atlas carry these records within their volatile makeup, preserving molecular traces of environments alien to our solar system. Yet even our most advanced instruments might miss signs of deliberate engineering if such engineering were intended to appear natural to civilizations at our current stage of development. A sufficiently advanced system could disguise itself within ordinary chemistry, its design indistinguishable from natural processes until observational tools reach a level far beyond what we now possess. The fictional framework of predictive collapse modeling serves as a metaphor for the real dilemmas of human civilization: climate change, dwindling resources, technological disruption, and geopolitical instability, all present risks that could threaten our long-term survival. It is reasonable to assume that any advanced civilization would develop sophisticated strategies to anticipate and mitigate such threats. If our speculative predecessors did exist, and if they truly deployed interstellar atmospheric delivery systems, they may have been responding to the same pressures we face today. In that light, efforts to restore Mars's atmosphere could be seen as a form of cosmic insurance, ensuring that worlds with the potential for habitability remain viable refuges, even after planetary catastrophe or technological collapse. This idea rebounds on us. What responsibilities do we bear as an emerging spacefaring civilization? Should humanity begin designing atmospheric restoration projects not only for Mars, but also for Venus, or for distant exoplanets that already exhibit potential habitability? Should we consider constructing backup systems, self-sustaining technologies that might aid in recovery if human civilization falters? These are not idle questions, for the DART mission in 2022 demonstrated that we already possess rudimentary tools of celestial engineering. We can detect hazardous bodies, predict trajectories, and execute interventions that alter orbits. These same capabilities, vastly expanded, could one day be directed toward atmospheric engineering rather than planetary defense. Testing the so-called desert supercomputer hypothesis would require searching for empirical signatures. Concealed networks of advanced computation, if they existed, might leave behind radio emissions, anomalous electromagnetic fields, or chemical imprints in desert aquifers caused by long-buried technologies. None of these signals have been detected, but detection methods grow more refined each year. LiDAR surveys, satellite-based ground-penetrating radar, and advanced geological imaging techniques may eventually uncover artificial structures invisible to earlier surveys. While no such discoveries have been confirmed, the ongoing expansion of our archaeological toolkit keeps the possibility alive as metaphor if not as evidence. The psychological appeal of predictive collapse models reflects our rising awareness of civilizational fragility. Humanity faces multiple existential challenges: climate disruption, nuclear arsenals, artificial intelligence risks, and cosmic hazards such as asteroid impacts. In that context, the notion that another intelligence has already solved these problems and seeded the galaxy with assistance systems offers undeniable comfort. Yet comfort and truth are rarely the same. The frameworks of quantum archaeology and desert supercomputers are evocative, but they remain metaphors rather than evidence. The genuine archaeological project humanity undertakes is more modest, but no less profound. It involves using ever more powerful instruments to observe the chemistry, timing, and behavior of interstellar visitors. Each new detection adds to a growing database of knowledge, and only through accumulation may patterns emerge that are invisible at present. 3i Atlas might ultimately belong to such a pattern, but that pattern will almost certainly concern the natural chemistry of interstellar space, rather than hidden networks of predictive computation. The universe has no obligation to give us neat answers or narratives that soothe our anxieties. Its challenge is different: to confront us with phenomena that test the limits of our models, while demanding that we hold fast to both scientific rigor and human curiosity. Perhaps the most important question raised by 3i Atlas is not what it is, but how we choose to respond to it. The comet's unusual chemistry and uncanny timing function as a kind of mirror, a test of our intellectual maturity. Do we leap toward comforting narratives that require nothing from us, or do we take the harder path of scientific inquiry, patient observation, and evidence-based understanding? The comet itself does not need to be deliberately designed as an examination in order to function like one. The universe has a way of confronting civilizations with puzzles that reveal their biases, test their patience, and expose the difference between rigorous curiosity and wishful speculation. How we meet these challenges will shape our trajectory as a scientific species. Consider the concrete tests now before us. Can humanity maintain funding for Mars sample return missions, even under political pressures and shifting budgets? Can we keep global survey networks active and transparent, despite their immense operational costs? Can we resist the lure of sensationalism that turns genuine mysteries into clickbait for fleeting attention? These questions are not abstract philosophy. They are practical choices that will decide whether human civilization develops the capacity to respond intelligently to genuinely anomalous phenomena. 3i Atlas, in that sense, becomes a trial of our collective ability to practice evidence-based decision-making under uncertainty. The successful DART mission offers a hopeful precedent. When faced with the reality of asteroid threats, humanity did not panic or dismiss the issue. Instead, it invested in detection systems, developed models of impact risk, and executed a controlled experiment in celestial engineering. By altering the orbit of Dimorphos, the DART mission proved that careful analysis, rigorous modeling, and targeted technology could produce measurable results. That achievement represents a disciplined contrast to the viral speculation that swirled around 3i Atlas, speculation that treated the comet as an alien artifact without evidence to support the claim. Social media amplified these extraordinary suggestions far more rapidly than measured science could compete. Algorithms rewarded the spectacle, and the result was a degraded signal-to-noise ratio in public discourse. NASA's approach provides a model for how institutions should handle such situations. Rather than dismissing the speculation with disdain or engaging in endless rebuttals, the agency issued clear statements grounded in evidence. It acknowledged what was uncertain while maintaining the principle that extraordinary claims require extraordinary proof. The near-term predictions about 3I Atlas provide opportunities to test this framework in action. As the comet approaches perihelion, solar heating should drive evolving ratios of carbon dioxide, water, and cyanide, revealing different layers of its nucleus. Post-perihelion, fading behavior should follow the established physics of comets. Any deviation would stand out. Artificial control systems, if they existed, might produce sustained non-gravitational acceleration, directed chemical release that does not correspond to solar distance, or even structured radio emissions. None of these signatures have been detected so far, and the scientific presumption remains that 3I Atlas is natural. To conclude otherwise would require unambiguous evidence that breaks with known physics. Global surveillance networks ensure that such evidence could not easily be hidden. The Atlas system, PanSTARRS, the European Space Agency's space-based observatories, and allied projects scan the skies with remarkable sensitivity. Independent confirmation across multiple instruments makes suppression or secrecy effectively impossible. If 3I Atlas exhibited incontrovertible signs of artificial origin, the data would be public within days, available to astronomers worldwide. This transparency represents one of humanity's great achievements in international cooperation, demonstrating that the cosmos itself is best studied as a shared human endeavor. The European Space Agency has taken the lead in providing regular updates on orbital calculations, observational campaigns, and planned Mars flyby monitoring. This flow of information enables the broader public to participate indirectly in the unfolding story, following developments in near real time. The educational potential is immense. Citizens who track these updates learn to distinguish between peer-reviewed analysis and speculative rumor, developing intuitions about how scientific consensus is built from evidence rather than spectacle. October provides two milestones. The 3rd of October, when 3I Atlas makes its closest pass by Mars, and the 29th to 30th of October, when it reaches perihelion. These dates create a kind of cosmic syllabus, moments when hypotheses can be tested, data can be gathered, and our collective response can be evaluated. Whether we meet these tests with rigor or with noise will say much about who we are becoming as a civilization that dares to watch the skies with both wonder and discipline. The dates ahead mark natural experiments, moments when the behavior of 3I Atlas will either confirm or challenge our understanding of interstellar chemistry and orbital mechanics. They are not appointments we created, but opportunities the universe has placed on our calendar. How we choose to interpret them will reflect the deeper character of our species. The contrast lies between transcendence and packaged solutions. Transcendence asks us to do the intellectual work. It demands that we wrestle with the complexity of cometary chemistry, orbital trajectories, and the inevitable limitations of observation from millions of kilometers away. It requires patience with uncertainty, a willingness to live with partial answers, and an openness to possibilities that may stretch our current frameworks. Packaged solutions, by contrast, deliver instant closure. Alien artifact theories offer immediate answers without requiring us to learn spectroscopy or orbital dynamics. They are appealing precisely because they allow us to bypass the difficult work of understanding. The moral weight of this choice extends beyond the mystery of 3I Atlas. It cuts to the core of how human civilization chooses to respond to cosmic phenomena. Are we building the intellectual tools to recognize the truly extraordinary when it crosses our path? Are we maintaining the telescopes, survey networks, and research institutions needed to examine such phenomena with rigor? Or are we shaping information ecosystems that reward speculation and spectacle over careful analysis, making it ever harder to distinguish between authentic discovery and manufactured controversy? The stakes are higher than they appear. As humanity expands its reach into space, we will inevitably encounter phenomena that defy our existing categories of physics, chemistry, and biology. Our handling of 3I Atlas offers a preview of how we may respond when faced with discoveries of far greater magnitude. If we can approach this comet with disciplined curiosity, resisting both panic and premature certainty, we signal readiness for the larger mysteries awaiting us in interstellar exploration. If we surrender to sensational speculation or comforting myths, we expose vulnerabilities that could compromise our ability to confront genuinely transformative encounters. The challenge is not to solve 3I Atlas definitively. Some mysteries may remain beyond the grasp of current instruments and methods. The true test is whether we can sustain intellectual honesty and scientific rigor when confronted by phenomena that resist neat categorization. Transcendence in this context means curiosity over certainty, evidence over rumor, collaborative inquiry over individual assertion. It means maintaining international cooperation, funding the observatories, and training the scientists whose work makes discovery possible. Packaged solutions will always be available. Alien artifacts, ancient astronauts, conspiracy theories, or dismissive skepticism provide easy answers that require no effort, no learning, no growth. Yet the universe seems structured to reward patience with understanding, investigation with insight, and curiosity with discovery. 3I Atlas is not only a comet, it is an opportunity to demonstrate the kind of species we aspire to be as we venture into a cosmos that will continually present us with phenomena stranger than anything we have yet imagined. October 3rd, 2025 represents more than a date on the astronomical calendar. On this day, 3I Atlas will make its closest approach to Mars, passing at roughly 30 million kilometers. This distance is close enough for the red planet's gravity to impart a subtle influence on the comet's path, yet far enough to rule out collision or dramatic interaction. For a brief span of hours, an interstellar visitor will occupy the same region of space traversed by Mars for billions of years. Two vast narratives of cosmic history will overlap. The ancient story of a planet that once held rivers, lakes, and perhaps life itself, and the contemporary story of alien chemistry arriving from stellar neighborhoods far beyond our reach. The European Space Agency's orbiters Mars Express and the Trace Gas Orbiter stand as our best tools for capturing this encounter. Both carry instruments finely tuned to analyze atmospheric chemistry, detect trace gases, and image small bodies in the Martian environment. If 3I Atlas reveals anything unexpected during its passage, these spacecraft are positioned to document it. The most probable scenario, however, is conventional, outgassing driven by solar heating. As the comet draws closer to perihelion later in October, carbon dioxide and water vapor should stream outward, forming a coma that expands and shifts according to the object's distance from the Sunday. Any significant deviation from these expected patterns could suggest something stranger, perhaps unusual nuclear composition, or, in the more speculative interpretations, artificial control. The emerald glow, reported in September, may intensify during the Mars approach. This could allow scientists to pinpoint the molecular processes responsible for the coloration, whether cyanide compounds, dicarbon molecules, or other exotic trace chemicals. Each detection would add a new layer to our knowledge of interstellar chemistry, providing insight into the processes that shaped 3I Atlas before it ever entered the solar system. Here, however, the narratives diverge. One is the speculative, terraforming fantasy, in which 3I Atlas behaves as though targeted, releasing concentrated jets of carbon dioxide toward Mars, or demonstrating gas emission patterns inconsistent with solar heating. The other is the naturalistic explanation, a comet following a hyperbolic orbit, governed only by gravity, and outgassing according to predictable physics. The unusual ratio of carbon dioxide to water, roughly 8:1, remains an important clue, but also a metaphor. Just as carbon dioxide can thicken a planetary atmosphere, premature explanations can cloud human judgment, obscuring evidence beneath layers of speculation. The intellectual challenge is to keep our atmosphere of understanding as clear as possible, allowing observation to pass through unwarped by assumptions. Trajectory models place 3I Atlas safely throughout its passage. Its closest approach to Earth will not occur until mid-December, at approximately 1.8 astronomical units farther than the Sun itself. This means no threat, only the opportunity for extended analysis once the comet emerges from conjunction. Yet the timing of solar conjunction adds a layer of dramatic irony. Just as the object reaches peak proximity to Mars and maximum solar heating, Earth-based telescopes will lose sight of it, blocked by the sunday. For several weeks, our most powerful observatories will be blind. To some, this invisibility fuels conspiracy thinking. But astronomical invisibility is not cosmic secrecy. Physics continues regardless of our vantage point. Solar heating will continue to sublimate volatiles from the comet's nucleus. Gravity will continue to shape its path. Any anomalous behavior occurring during the unseen window will leave imprints, detectable once observations resume. The European Space Agency has been notably transparent about the observational challenges and opportunities. This distinguishes 3I Atlas from earlier interstellar visitors, which swept through the solar system without close approaches to major planets. This time, we have the chance for comparative analysis of interstellar chemistry in the environment of a potentially habitable world. By late November, as the comet emerges from conjunction and begins its post-perihelion arc, observations should reveal how solar heating has transformed its chemistry and appearance. Instruments will measure whether carbon dioxide remains dominant, whether new compounds have surfaced, and whether the green glow persists or fades. The comet's encounter with Mars will pass, but the data it yields will remain, offering humanity a rare glimpse of interstellar material, interacting however indirectly with a planet that once held the conditions for life. Comets follow a familiar rhythm. As they approach the Sun, surface volatiles sublimate, producing luminous comae and streaming tails. As they retreat, activity declines, their surfaces left depleted and inert until the next return, if there is a next return at all. Any significant deviation from this established pattern signals something unusual, whether an uncommon nuclear composition or, in the most speculative interpretations, artificial modification. Mars adds another dimension to this story. The Mars Sample Return mission, despite recent delays, remains scheduled for the early decades of the 21st century. If successful, it will deliver to Earth the most valuable cargo ever retrieved, carefully chosen specimens from Jezero crater, where Perseverance has already identified potential biosignatures. These samples could provide definitive answers about ancient Martian life, evidence preserved in stone that might rewrite our understanding of biology beyond Earth. Should such answers arrive, they will also reshape how we interpret interstellar visitors like 3I Atlas. What appears now as chemical curiosity could one day be recognized as part of a deeper planetary narrative: how life emerges, how atmospheres evolve, and how biological recovery might unfold after climate catastrophe. Yet, we must resist premature connections. The discovery of ancient biosignatures and the arrival of unusual interstellar chemistry may be linked only in our minds, meaningful to human storytellers but irrelevant to cosmic mechanics. The universe does not arrange itself to satisfy narrative coherence. Its patterns belong to physics, not to myth-making. The encounter at Mars is therefore about more than 3I Atlas itself. It forces a choice in how humanity engages with cosmic mysteries. One path is scientific: to continue monitoring with the instruments we have, to publish observations transparently, to refine our conclusions in step with accumulating data. This path acknowledges uncertainty, insists on extraordinary evidence for extraordinary claims, and resists the temptation to satisfy curiosity with stories unanchored in proof. The other path is speculative: to weave narratives onto incomplete data, emphasize coincidences over probabilities, and allow wishful thinking to masquerade as analysis. On that path, patterns will be found whether or not they exist in the measurements. The true pivot lies not in the behavior of a single comet, but in our response to it. Are we capable of meeting anomalies without surrendering to psychological comfort? Can we hold on to curiosity without collapsing into certainty? These questions have lingered at Mars for billions of years, inscribed in the riverbeds and mineral scars of a once-living world. Now they return in the guise of an interstellar traveler, passing briefly near the red planet while Earth, hidden by the sun, is unable to watch. When 3I Atlas sweeps past Mars, the encounter will measure more than orbital trajectories and chemical ratios. It will measure us. The interpretive framework we choose now will echo into the future, shaping every response to the mysteries that will come. By observing this comet, we are also observing ourselves, testing the intellectual integrity that must guide us into a universe vast enough to confound every easy story we try to impose upon it. In the shadow of Mars, something ancient exhales into the void. From the deep past of another sun, 3I Atlas breathes out carbon snow, its vapors curling into the dark, carrying a chemistry that speaks in molecular languages we are only beginning to decipher. The cadence of cosmic coincidence has carried us here, an interstellar visitor rich in atmospheric restoration compounds, arriving precisely as humanity uncovers its strongest evidence yet for ancient life on the red planet. The facts, stripped of embellishment, stand firm. 3I Atlas did not originate here. Its hyperbolic trajectory and excess velocity prove that it came from beyond the solar system, and that when its journey through our neighborhood ends, it will depart forever into interstellar night. Its coma reveals unusual chemistry, with a carbon dioxide to water ratio of roughly 8:1, among the highest ever recorded in any comet. It will sweep past Mars at a safe distance of 30 million kilometers on October 3rd, reach perihelion within Mars's orbit on October 29th and 30th, and remain invisible to Earth-based telescopes during this most critical phase of its passage. Equally clear are the limits of our knowledge. No evidence confirms that 3I Atlas is a product of engineering, or that it serves as a delivery system for planetary restoration. There are no signals, no artificial signatures, no indication of intelligence beyond the elegance of natural chemistry. The popular stories, alien artifacts, DNA activation, cyclical returns every 3,600 years persist because of their psychological power, not because of data. Still, coincidences have a way of unsettling even disciplined skepticism. The timing, interstellar chemistry arriving at Mars just as biosignatures are reported in Jezero crater. The content: carbon dioxide, water, organics, precisely the mix required for atmospheric restoration. The geometry: maximum intrigue at the moment of minimum visibility, with the comet hidden behind the Sun during its closest and most active phase. These patterns might signify nothing beyond our evolutionary impulse to detect relationships in complexity. The universe often appears designed until its mechanisms are revealed, and then design collapses into physics. At this crossroads, we face a choice larger than 3-1 Atlas itself. One path is transcendence, patient investigation, collaborative research, evidence-based understanding. It asks that we fund the observatories, train the scientists, and maintain the fragile fabric of international cooperation. It requires tolerance for uncertainty and the courage to hold open possibilities that might reshape our frameworks. It demands the labor of learning spectroscopy, orbital mechanics, and atmospheric chemistry, rather than surrendering to easy stories. This path passes through European Space Agency updates, NASA bulletins, and the peer-reviewed papers that will record the comet's behavior during its Mars encounter and its evolution beyond perihelion. It insists we separate institutional science from social media noise, genuine uncertainty from manufactured controversy. The other path offers safety. Alien artifact theories and ancient astronaut tales give instant explanations, soothing anxieties, while eliminating the need for understanding. They promise that someone else has already solved the problems that confront us. They allow comfort without growth, narrative without knowledge. 3-I Atlas thus becomes more than a comet. It becomes a mirror, reflecting the kind of civilization we are becoming, testing whether we choose transcendence or safety as we learn to meet the mysteries of the cosmos. Government conspiracy theories suggest that all mysteries already have answers, but those answers are deliberately hidden from us. These explanations are comforting in their simplicity. They demand no effort beyond belief. We are not asked to study spectroscopy or orbital mechanics, not required to fund expensive instruments or train specialists, not called to cooperate across nations and disciplines. Instead, we are offered the illusion of understanding without the labor of discovery. But the universe does not appear to reward passivity. It seems to reward curiosity with discovery, investigation with insight, and patience with genuine understanding. The detection and study of 3-1 Atlas mark an important milestone in humanity's journey toward that understanding. Every spectroscopic analysis of its chemistry, every refinement of its hyperbolic trajectory, every recorded change in its coma adds to our expanding knowledge of how matter behaves on interstellar scales. The comet itself may not hold final answers, but the process of studying it produces revelations. By forcing us to improve our instruments, refine our methods, and collaborate across borders, 3-I Atlas becomes a catalyst for intellectual growth. As detection networks continue to improve, we will inevitably discover more interstellar visitors. Each will bring data chemical fingerprints, orbital dynamics, behavioral anomalies that expand our frameworks for understanding objects formed around distant stars. Over time, these fragments accumulate into patterns, and patterns into theories. In that context, the Mars sample return mission acquires new weight. Whenever it finally occurs, the samples collected from Jezero crater could offer definitive confirmation of ancient Martian biology. If the leopard spot textures in Martian mudstones prove to be genuine biosignatures, then the chemistry carried by 3-I Atlas will be reframed as part of a larger narrative. How planetary habitability emerges, how atmospheres evolve, and how biological recovery might occur after planetary collapse. Even if Mars does confirm ancient life, And even if future interstellar visitors share the unusual atmospheric chemistry of 3I Atlas, we must be careful not to impose teleology where none exists. The universe may be more supportive of life than we currently recognize, yet not necessarily designed with intention that resembles anything we can name. It may simply be that the conditions for habitability arise more often than we expect, not that they were planned. The choice between transcendence and safety is not an abstract philosophical exercise. It has direct consequences for the future of human civilization. If we embrace transcendence, rigorous investigation, evidence-based analysis, and disciplined curiosity, we will build the intellectual and technological infrastructure needed to recognize genuine anomalies when they appear. If we fall into safety premature, certainty, and narratives that soothe rather than challenge, we risk shaping mental frameworks that blind us to discoveries that fall outside our expectations. The universe may present phenomena far stranger than anything we can now imagine, and our response to 3I Atlas is an early rehearsal for those transformative encounters. As the comet completes its unseen encounter with Mars and begins its post-perihelion retreat, months of additional observations will refine our understanding of its chemistry and behavior. If the data confirm our natural comet hypothesis, we learn. If the data reveal anomalies that challenge existing models, we also learn. In both cases, the transcendent approach succeeds because it deepens human understanding and expands our investigative capabilities. The safe approach succeeds only if reality aligns with our preconceptions, an outcome that nature rarely guarantees. So what is 3I Atlas doing as it passes through Mars's orbit? Exactly what natural law dictates, following its hyperbolic path, sublimating volatiles under solar heating, and expressing a chemistry shaped by its birthplace around another star. Anything more is projection, reflections of our hopes and fears cast onto a canvas of cosmic processes. The final choice belongs not to the comet but to us. 3I Atlas continues its ancient journey, carrying chemistry from stellar neighborhoods we may never reach. Whether that chemistry proves to be coincidence, design, or something beyond current categories, the universe waits with indifference and patience. Our responsibility is to develop the tools and the intellectual discipline for genuine comprehension. The consequences of that choice will shape every future encounter, guiding us through mysteries that test the limits of imagination in a cosmos vast enough to contain both profound meaning and magnificent indifference.